The main objective of this lab is to observe the effect of drag on two objects compared to the force of gravity alone on the object. We use the momentum principle derived as shown to find the final momentum and the final velocity. We also use the position update formula, which is final position equals initial position plus final velocity times change in time. Here, the F net is gravity. This is my tracker where I show the cotton ball falling. The X and Y axis orientation is the normal orientation with positive Y being pointing up and negative Y being pointing down. The red dots are the movement of my cotton ball, and I have my scale set. You can see in the right corner the graph of time versus Y position. It's a straight line. And then I took the data on the right hand side and copied and pasted it into Excel. In VPython, I use the position and velocity update formulas to calculate the theoretical velocity and movement of my cotton ball. I had to update the ball mass, and I had to update the end time. The change in time is the same. Also, I took out the force of drag because now we're only looking at the force of gravity. When I ran my code, I got this graph and this picture. In Excel, I took the data from my code and I plotted it next to the data from Tracker. The blue dots are the data from Tracker and the red is the data from my code. As you can see, the red goes down much quicker than the blue. This is because of drag. Next, I analyzed the movement of something that drops quickly with very little air resistance or drag. The orientation is the same. The red dots are the path of the object, and I have my scale. And I took the data from the right-hand side and copied and pasted it into Excel to make a scatter plot. I changed my code in VPython the same way that I did for the cotton ball. I updated the mass and the end time based on my tracker data and the mass of my water bottle. And then I plotted the two data sets next to each other. As you can see, they're pretty similar. This shows that the force of drag does not have a very big impact on the water bottle because it doesn't have very much air resistance. Next, I put force of drag into my VPython code. The formula for force of drag that I used is -b, which is a constant, multiplied by the magnitude of the velocity, multiplied by the velocity vector. I then added that to my F net and ran my code. I plotted the data in the green, and as you can see, it's a much better fit for the original data. I also updated my code with the F drag for my water bottle. As you can see by the arrows, the force of gravity is much larger than the force of drag on the water bottle as shown in the original plot. I plotted my data that included the force of drag, and as you can see, it's very similar to just the force of gravity because the force of drag is so small, it's pretty much negligible on the water bottle. As shown previously, the object that dropped slowly, the cotton ball, had a much better fit with the tracker data when the force of drag was accounted for. This means that the force of drag model predicts the terminal velocity much more accurately than the model. For the what if question, I wrote a program to model the cotton ball dropping if it was thrown. As you can see, the red line is if it was thrown. What I did was I added an initial velocity to my VPython code and then I ran it, and this is what I got. It does not reach terminal velocity, although if given enough time, it would reach a terminal velocity, but within this data set, it doesn't. Now looking back at our main objective, we see that we accomplished the main objective, and we know that objects with a lot of air resistance have a greater force of drag, and objects that fall quickly and do not have as much air resistance have a much smaller force of drag.